So now let's go ahead and talk about some ways of actually trying to implement these graph ideas in a concrete data structure. So what structures can we use to actually represent these relationships between nodes and edges? Now, before I can get to that, I have to give us one little caveat on how we've been talking about efficiency so far. So one of the things we're going to end up needing for graphs is this thing called multivariable analysis. So what I mean by that is when we're thinking about algorithmic analysis, so far we've thought of everything as being in terms of a single input size or argument n. Sometimes it's the own parameter, other times it's the size of the structure, but there's no reason we can't do this kind of reasoning about scale in terms of multiple inputs. So why are we going to allow multiple variables here? Well, remember, algorithmic analysis is just a tool to help us understand code. Sometimes it's helpful to understand more about kind of our structures by making bounds that are related to multiple factors rather than trying to kind of separate those out into separate cases. And this will be a little bit clearer in the example I'll show. And this is going to help us a lot with graphs when we have very natural multiple ways to change the size of a graph. You can either add more nodes, you can add more people to your social network, or you can add more edges, you can add more relationships between people. And it turns out that some algorithms actually run on the degree of some of the nodes. So for example, how many edges are coming out of a particular node. So there's lots of different factors that come in play here. And so it might help us to beef up our tool a little bit in order to work with these multiple input cases. So all that's really going to change is what we come up for in terms of our runtime functions. Remember, before I told you that a runtime function had to have a single input n, and it would output the number of steps it would take for any input, whatever that input n is. Now what we're going to do is when we have multiple variables that we can easily change around, we could extend this notion of the runtime function to be a function that takes multiple variables. So in this example here, I bumped my table, sorry. In this example here, we might think about some code that runs in terms of the size of two different lists. We might call the list 1 to have size n and list 2 to have size m. And it might be the case that the runtime will be dependent on both of those variables, not just the inputs, one of those input sizes n. So this doesn't remove the need to have something like case analysis. We can still make separate cases for things that don't quite fit into the formula, that really make sense to analyze separately. But in each of those cases, we'll now have two free variables. What's this n? What's this m? We come up with a function in terms of both, and then we can still do asymptotic analysis on that. So we could come up with runtimes like big O of n times m to say it scales like with the multiplication of both. It gets a little bit more tricky of like, what does the actual big O definition look like in this case? So we're not going to worry too much about this, but using our intuition of what big O means, it means it's going to be upper bounded by something like n times m. So as this is growing, this is kind of how it scales. So all we're really doing here is really just saying that we're allowing multiple variations to determine our runtime. And again, if you have separate things that affect runtime other than just input size, you still use case analysis. You could still come up with a best case or a worst case or any other case. But now the function that you might come up with will be in terms of multiple variables. So we lied a little bit when we said you had to have a single variable in your runtime function before. This is kind of the full truth, where you allow it to have multi-variables depending on how many inputs you actually have here. Now, so what we're going to do now is actually talk about how can we use this idea of a multivariable big O bound to analyze an implementation of this idea of a graph. So one way to represent a graph in a concrete structure is what we call an adjacency matrix. An adjacency matrix is kind of forming a really large table where there's an entry, a row, and a column for every node in the table. So notice in this graph up here, I have nodes 0 to 6. So I'm going to have a 7 by 7 table because 0 to 6 is 7 numbers. And this matrix here, we're going to use to store information about the edges. So in an adjacency matrix, we're going to store a 1 whenever there is an edge from one node to another. So if there's ever an edge from U to V, we're going to store 1 or something like that in the entry for this position. Now, if this graph is a undirected graph, then pretty naturally, this matrix will have to be a symmetric one, where if we ever talk about the edge between 0 and 1, if it's an undirected graph, it just makes as much sense to have an edge from 1 to 0. So if the graph is undirected, it will make sense for this matrix to actually be symmetric. But in general, for undirected graphs, we can have the same idea where, or have an idea where you have an entry at index UV if there's an edge going from U to index V. So if I represent it in this way, let's think about what are the various runtimes of operations that we might want on a graph. For example, how long does it take to get an edge from this graph, to add an edge to this graph? So if we're trying to add an edge, it's really just about going to this index in the matrix and adding something there. So for example, if we're trying to add an edge from, whoops, my pen is continuing to not work. I just fixed this a second ago. There we go. So we're going to have an edge from 1 to 4. Well, that's really just going to change index 1, 4 from a 0 to a 1. Similarly, because it's an undirected graph in my context, I should also change 4, 1 to be a 1 here as well. Okay. So adding an edge will just be constant time. Assuming we have this like 2D array structure, just like an array, you can instant access into something. Now, what if you want to remove an edge? Similarly, this is going to also be an O of 1 operation. We just index into that spot and set a 1 to a 0. And if you want to check if an edge exists in this graph, you could just say, look at the index UV, and it'll tell you if there's a 1 and a 0. So this adjacency matrix is really nice because for a lot of these query and modification operations, it's really just kind of a O of 1 runtime. So what if you want to figure out how many out neighbors of U are there? So again, remember this adjacency matrix can represent an undirected or a directed graph. So it kind of makes sense to ask what are the out neighbors in any context here, like what edges come out of it. Since we have this structure set up to index kind of UV like this, we can imagine that if we want to find all of the out neighbors of U, say U is in index 3 for our example, we would just look at the row 3. And we would find any entry that has a 1 and report back, these are all of the nodes that are out neighbors of U. And again, because this is an undirected graph, the in neighbors are going to be symmetric, but you could imagine an undirected graph that ones aren't going to line up exactly the same. This second point is supposed to say what are the in neighbors of V. I'll make sure to change that on my slides that I post on the website. If you want to find the in neighbors of V, we'll say we're looking at maybe node 4. Well, we just look at this column here and say, okay, what entries here have the number 4 in it? Now, both of these operations here are going to be kind of based on the runtime of how many nodes there are in the total graph. So for example, this kind of works on iterating over an entire row or entire column. And we said here that this matrix is going to be n by n. It's going to have a row and a column for every vertex. So this runtime is really going to be bounded by this, this O of n, which is okay. What about the space complexity? How much space does the structure take up? Well, it takes up space proportional to n squared, right? We have this table that's n by n. It's going to need something like n squared spots to fill that out. So this structure is actually very space inefficient because it has to store zeros all over the place for all the edges that aren't there. So we'll see an alternative representation, kind of another kind of, in some sense, the other extreme, is this thing that we call an adjacency list. Very similar idea in some sense of trying to represent this, but it tries to save a lot more space. So the idea is to create a list of kind of one index for each node. We'll maybe call that a map instead. So we have this kind of mapping from the nodes to all of the nodes that they have an edge to. So in this adjacency list, we have this kind of something that looks like a hash map here, where the index for A has a list of all of A's neighbors, all of the nodes that A is connected to. So A is connected to B and C, so B and C appear in its list. So we call this an adjacency list representation because each index stores a list of its adjacent nodes. Similarly, if we are thinking about a directed graph, then the adjacency is not a symmetric property, right? A being adjacent to B is only one unidirectional because it's a directed graph. If it's an undirected graph, then it makes sense to have this be symmetric, and you'd also store A in B's adjacency list. So this kind of other representation of this graph kind of takes a different approach to how to talk about this. So when it comes time to adding an edge, this could be relatively straightforward. You could just go in and say, okay, if I want to add an edge from A to D, I just go into A's bucket and add a node D. That could be very straightforward. But if you want to remove an edge, that might involve looping through all of the edges that are there and removing the one that you find. In the worst case, this is going to end up being something like big theta of the degree of the edge of the node you're looping through. So you're going to have to loop through all of its edges. So worst case removing actually takes some time. Similarly, to check if an edge exists, you're going to have to search that whole list for your start node. So you can see here that we'll talk about those other operations in a second, but you can already start to begin to see that this, in some sense, this implementation is slower because we have to do this looping in order to kind of do anything with removing or checking if an edge exists. Similarly, if you want to get the out neighbors of U, we're going to have to actually go to that bucket and scan through all of the nodes there to get all the out neighbors. But it does tell us that information relatively straightforwardly, right? Because we're storing all the out neighbors in the adjacency list. But then when we want to get to the in neighbors, that's supposed to say in neighbors there. Now this is where things get worse. We have to use an n plus m operation. Now, before I explain what that runtime means, let's talk about how would we implement in neighbors. Well, if I want to find the in neighbors to A, all of the nodes that point to A, I can't just look at A's bucket because that just tells me all the nodes that A points to. So what I'm going to need to do is go to each bucket and scan through its whole list to find any A's there to find all the nodes that point to A. Well, since there are n vertices, n nodes, this loop over the buckets, 0, 1, 2, 3, that's going to take n time. And then you're also going to have to, over all of those buckets, loop over every edge in the graph. You have to check all of the edges coming out of A, all of the edges coming out of B, all the edges coming out of C, etc. In total, that's going to end up being m edges you have to check. And so this runtime is actually in terms of both. It's in terms of the number of nodes plus the number of edges, n plus m. It's kind of linear in both of these variables. And so this is why we introduced this idea of multivariable analysis. We need to talk about both of them. This will look weird at first, but I promise we'll get lots of experience talking about runtimes that have this format. What about the space complexity here? How much space does this take up? This also takes up n plus m space. You need an array of size n to store all of the buckets, and then you need to store a linked list or something. And in total, those links, there's going to be m of them because each link or each node in those links represents a single edge. So in total, there will be m. So it takes n plus m space in total. Now, I want to mention one third-ish way of representing these structures that kind of tries to satisfy, in some sense, the best of both worlds, at least hopefully. You can usually use hashing as kind of an in-between solution here. It's not quite an adjacency matrix. It's not quite an adjacency list. It's kind of in the middle. So usually a very common way to represent this, like in your code, is to make something like a map from node to map of node to edge label. And this is in some sense trying to get this adjacency matrix-like property, but it doesn't waste all that extra space. Now do remember, if you're using these hash maps, they do take a little bit extra space behind the scenes to make that hash table, but it's not completely using that whole n squared space, and it can resize as needed. So it's not quite as uses much, it doesn't use quite as much space as the adjacency matrix, and its operations tend to be fast like the adjacency matrix most of the time, at least in practice. So we end up with runtimes that are constant time for most things. Then getting the out neighbors and in neighbors of something take about the amount of time we would expect. Out neighbors, we just have that information stored for us. This is stored in some sense a lot like the adjacency list, where you have like mapping one node to the set of nodes that it maps to. And so to get the in neighbors, it might not be optimized for this in a directed graph. And so you're going to have to search the whole table. So you kind of get that. But the space complexity can still be kind of this linear space complexity. It's not n squared. It's more like n plus m. Now, again, it's hiding constant factors, especially because these hash tables use a little extra space, but it's not going to be kind of this n squared world. So which one of these three should you use? Well, adjacency matrices do take a lot more space. So is there a case you'd ever use them? Well, yeah, we saw that those operations, many of those operations, were really, really fast. If you know your graph is a dense graph, meaning the number of edges is already close to n squared, meaning that most nodes are connected to other nodes, then the running time is worth it, since you're already going to be using that space requirement anyways, right? In that super dense case, the adjacency list will still take just as much space as the adjacency matrix, because you have to store all of those n squared edges. And the constant factors for matrices tend to be better because they're array structures, just like all that memory stuff we talked about earlier. And sometimes, we won't talk about this too much, but we might have a day that we can talk about this in class. We can sometimes use this matrix to actually tell us really useful information about the entire graph structure using this thing called spectral graph theory. Very interesting, more modern field of graph theory. Really, really cool, but not a core learning objective in this course. Now, what's the trade-off between using that linked list version of the adjacency list and this kind of in-between hashing version? Well, that hash table I said was O of 1 or theta of 1 and the add and remove and all those other operations. But remember, that's an in-practice assumption. You can still hit that worst case, which would not be the best. You can still get some pretty slow runtimes. And the linked list structure won't necessarily give you those kind of fluctuations that hashing might, but they actually have this benefit of kind of really being a compact representation. Most of our graph algorithms don't need to look up an arbitrary edge. Usually they're just iterating over all edges, and that adjacency list representation nicely provides that for you. You don't have to kind of loop through all those empty buckets like adjacency matrix or that hashing implementation. Now in 373, we're just going to assume, unless we say otherwise, that we're going to be using this kind of hashing implementation and that all operations are O of 1. So we're always going to assume that we're getting this in practice case. We're going to assume that worst case won't happen. So unless we tell you otherwise, assume we're using that hashing structure. Now, this video has been going on for a little longer than I originally planned, so I'm going to save this ST connectivity stuff for it's kind of the warm-up for the next set of videos where we start talking about algorithms that operate on these graphs. So I hope to see you all in class today, where we can talk about these applications and terms of graphs.